Welcome to the Deep Dive Books channel, where we hope you find something valuable every day.
Recently, Google unveiled a new quantum chip, named Willow. It claims to solve in 5 minutes what the fastest supercomputer today would take 10 to the 25th power years. An unfathomable number exceeding the age of the universe. This announcement caused a stir. This is a remarkable breakthrough, a qualitative leap, rather than a quantitative improvement. It's not just conquering a peak, but opening vast new horizons, possibly worthy of a Nobel Prize. Yet, it might not be as extraordinary as you imagine. Today, let's temper expectations before building excitement. We'll first discuss what quantum computers cannot do, and then examine the true significance of this breakthrough. By the end, you'll have a clear perspective on quantum computing advancements. Previously, in our series on quantum mechanics, we touched on quantum computing. Here's a more accessible explanation. Why are quantum computers faster than classical ones for specific tasks? The core reason lies in quantum bits, qubits, and their superposition states. In classical computing, a bit is either 0 or 1, representing a single value. In contrast, a qubit can be in a superposition of 0 and 1. Essentially both simultaneously. It can represent any proportion of 0 and 1, such as 30% 0 and 70% 1, or 49% 0 and 51% 1. To understand superposition, you'd need a deeper dive into quantum mechanics. For now, the key is this. A quantum circuit can represent many states simultaneously, unlike a classical circuit that represents only one. This means that a single operation on a quantum circuit can perform what would require numerous operations on a classical circuit. Let's use an analogy to make this clearer, though it's not perfectly precise. Imagine a lake with a light source at point S above the water and a target point D below the surface. We want to find the path light takes from S to D. It's not a straight line because light refracts at the water's surface. Question is, where does the refraction occur? Classical computation works by testing every possible refraction point on the surface, calculating all possible paths to determine the fastest route. This requires an enormous amount of computation. Quantum computation, on the other hand, is akin to performing an experiment, where light simultaneously explores all possible paths from S to D. The resulting path is a superposition of all potential routes. The wave functions of these paths interfere, leaving only the fastest one. While the real path here is singular, in other cases, the solution may be a probability distribution. Classical methods compute one by one, while quantum methods process all at once. That's the fundamental difference. This idea is simple, but building a quantum computer, choosing a problem, and having it outperform a classical computer, formerly known as a classical computer, is no easy feat. In 2019, Google achieved this by tackling a problem specifically designed for quantum computers. The problem is called random circuit sampling. Imagine a quantum computer circuit made up of multiple quantum gates, analogous to logic gates in classical computing. Now, configure a random circuit with some quantum gates, set all initial quantum states in the circuit to 0, let it evolve for a while, and ask, what will the final result be? The answer is a collection of zeros and ones in various combinations. Due to quantum randomness, the outcomes vary, so multiple experiments are needed to determine a probability distribution. For a classical computer to predict this distribution, it must consider the probability of every gate and all possible circuit paths. An astronomical task. For quantum computers, this is a natural quantum event. Running the circuit once provides a result, and repeating it yields the probability distribution. Thanks to quantum interference, irrelevant paths are filtered out, requiring far fewer computations than classical methods. The key is that quantum computers utilize natural quantum evolution, while classical computers require exponential resources to simulate quantum states. For this specific problem, a quantum computer with sufficient quantum gates will inevitably outperform a classical one. In 2019, Google's quantum chip achieved this with random circuit sampling, marking the realization of quantum supremacy. meaning superiority in this tailored task, not the mistranslation as quantum hegemony seen in some media. The 2024 Willow chip repeats the feat with a more complex chip and the same problem. Fundamentally, it's not a different achievement. Boasting about solving a task requiring 10 to the 25th power years for a classical computer is misleading because the problem is tailor-made. It's like me setting a task that no AI can outperform me in. Imitating myself. No algorithm can mimic me better than I can. Random circuit sampling is a valid problem, but it doesn't mean quantum computers now threaten classical computers. The reality is that quantum computers cannot solve all classical computing problems. They are limited to specific types of tasks. To utilize a quantum computer, you must first develop a corresponding quantum algorithm. So far, scientists have discovered very few quantum algorithms, each solving a specific problem. For example, Shor's algorithm enables quantum computers to perform prime factorization. Since modern encryption relies heavily on prime factorization, in theory, quantum computers could crack codes. Some even claim Google's chip threatens Bitcoin. This is highly exaggerated. Current quantum computers would need millions or billions of qubits to achieve this. At present, they can only factorize small numbers, like 3 by 5 or 5 by 7. Another quantum algorithm, Grover's algorithm, aids in search tasks, finding the most likely solution among many inputs. Classical computers must test options one by one, whereas quantum computers can test all options simultaneously. One promising use of quantum algorithms lies in linear algebra operations, like matrix multiplication. The key is that quantum algorithms must be invented one at a time. There's no systematic way to translate classical operations into efficient quantum counterparts. Moreover, many basic classical operations, like copying a bit or accessing specific memory locations, are challenging for quantum computers. In some cases, classical methods remain faster. Thus, quantum computers won't replace classical ones. They excel in solving niche problems, such as simulating complex physical phenomena, molecular modeling, supply chain optimization, financial risk analysis, and drug synthesis. Will quantum computers replace GPUs for training large language models? Unlikely. While they can accelerate linear algebra operations, handling training data and outputs involves classical information, which quantum computers struggle with. A popular quip circulating online says, quantum computers are GPUs over the multiverse. Famed physicist Max Tegmark also remarked that running ChatGPT on a quantum computer would mean the AI experiences countless scenarios simultaneously, proving the multiverse exists. Let's clarify. Such claims are philosophical musings, or poetic interpretations. Quantum computers, no matter how advanced, cannot prove the many-worlds hypothesis. While quantum mechanics has a many-worlds interpretation, proposing that every quantum event splits reality into parallel universes, it remains untestable and purely theoretical. The key point is that quantum computers, no matter how efficient, do not harness power from parallel universes. Energy conservation holds true. Quantum computers cannot transport you across universes. So, what's truly groundbreaking about Google's achievement? It solves two fundamental challenges. As mentioned, quantum computers require qubits to maintain coherence. Synchronized wave functions in resonance. Any interference disrupts coherence, which becomes harder to maintain as qubit numbers increase. This is why real-world cats cannot exist in Schrödinger's superposition of life and death. They're too large and decohere instantly. Yet, Google's new chip has more qubits than its predecessor, with coherence time increased from 20 microseconds to 100 microseconds. A bigger challenge lies in error correction for quantum chips. All computers, including classical ones, occasionally experience bit errors, which necessitates error correction. The simplest approach is to back up each bit. However, quantum bits, qubits, are more prone to errors, and quantum mechanics prohibits directly copying a qubit, making error correction much more complex. There was even a belief that scientists would struggle with the issue of quantum error correction for decades to come. However, Google has developed real-time error correction, where adding more qubits reduces error rates. Compared to its predecessor, Willow's error rate is 20 times lower. The method involves grouping qubits into arrays, like 3 by 3 or 7 by 7 grids, called logical qubits. Errors in individual qubits within the grid can be corrected collectively. Larger grids lead to lower error probabilities. I don't fully understand the specifics, but the idea seems to involve grouping several qubits into a 3 by 3 or 7 by 7 matrix, referred to as logical qubits. In this setup, even if one qubit in the matrix fails, it doesn't matter. The larger the matrix, the lower the error probability. By combining extended coherence and real-time error correction, Google has demonstrated that larger quantum chips become more stable and error-resistant. This marks a turning point. Quantum computing can now scale effectively. In summary, quantum computers remain in their infancy, but Google's breakthrough shows their immense potential and viability. Quantum chips are no longer experimental toys for a handful of physicists and engineers. They are poised to become a serious business. That's it for today's content. Thank you for watching, and I'll see you in the next video.
If you feel there is value in this, please like, subscribe to this channel, and leave your thoughts or suggestions in the comments section. Let's grow together and read more good books.